A very interesting application of nuclear radioactivity is when we use the properties of carbon-14, the radioactive nature of carbon-14, to be able to calculate the age of a specific artifact that once was alive. So again, radioactivity has many applications: cancer treatment, imaging in medicine, nuclear power plants with its controversies as well, but also to determine the age of something that was once alive or was able to absorb carbon from the atmosphere in form of CO2. So let's talk a little bit about not only the equations but the background of the theory that allow us to calculate the age of something that was once alive. So first of all, one must know that carbon-14 is naturally produced in the atmosphere when neutrons, let's put a neutron here sometimes, and there's a proton, when neutrons created by cosmic rays in the higher levels of the atmosphere impact atoms of nitrogen and create carbon-14. This is also a nuclear reaction. Notice that it should be balanced, but what's important here is that there is a certain amount of carbon-14 in the atmosphere that will of course become CO2 like any other carbon. Notice that the isotope carbon-12, carbon-13, carbon-14, they all have the same chemical reactivity. Only one is a little bit heavier than the other, but from the chemical point of view, there will be very little difference. So a steak made out of carbon-14, it will taste the same to you than a steak made out of carbon-12. What we were saying then is that carbon-14 will be incorporated into CO2 and plants will make it as such. So imagine there is a tree here and there is some carbon-14 in form of CO2. This will be absorbed and the tree will be eaten by an animal. Wish me luck if let's say that this is a cow, and then here comes a man that eats a cow, whatever. So as you can see, carbon-14 can jump from one living species to another, and this transfer happens just in the range of 100 years, not longer. So actually less than that. Hopefully you don't want to eat a cow that is 100 years old, but it should not take much time from the incorporation from CO2 until whoever of this that was alive is now dead. So we can use the radioactive nature of carbon-14 to measure how old what is that species, or how long ago that species was alive. And this is the nuclear decay of carbon-14, and it follows also, like any other radioactive decay, a first-order reaction. The half-life is almost 6,000 years. It means that every 6,000 years the number of nuclei is being halved, and the equation is pretty simple, with one caveat. It's important if you really want to do a very specific calculation, you have to correct this because you assume that N0 is known. In other words, you know the concentration or the amount of carbon-14 in the atmosphere, in the atmosphere when that tree, cow, or person was alive. That may not be the case, so one has to calculate in an indirect way the amount of carbon-14 at that point, or at least introducing some corrections. The corrections are minimal. It's not going to change by thousands of years the result. Okay, so let's practice a little bit. First of all, let's see the extent of aging that we can calculate. Notice that if you plot logarithm of n for a first order reaction versus time, you get a straight line. The slope should be minus k, which is related to the half-life. Typically we can date things up to tens of thousands of years, not longer. So let's talk a little bit about that. Let's talk about the limit that carbon dating allow us to detect? For example, if our instrument, and it will all depend on the instrument, but if our instrument cannot detect farther than a 0.20% of its original value, in other words, if the ratio of initial number of carbon-13 nuclei and the current has to be around the 0.20%, what is the maximum amount of time that we can detect? Notice that this will be minus kT, okay, and K is related to the half-life. This we're giving here the half-life, so this is logarithm of 2 divided by the half-life, which is 5,715 years. Okay, so if our limit is this much, what is the time? The time will be, this is minus logarithm of 2 divided by 5715 times t. Okay, so let's take logarithms on both sides. Logarithm of 0.2 over 100 is equal to negative logarithm of 25715 times time. Therefore, the time is logarithm of 2 divided by 100. Sorry, I'm mixing things up. Careful here. I just don't want to use a calculator so that you know where all the numbers come from. Minus logarithm of 2 now divided by 57. This will be the maximum amount of time, or the oldest sample that we can use to specify the age that that sample has.